Hey guys, just to let you know, this lesson is in collaboration with Flip Academy, a free online platform for all of your GCSE, A-Level, IB and CBSE revision, out now on web at www.flip.academy, and also as an app for Apple, iOS and Android. It really is better than all the other GCSE platforms out there. It covers all the topics in great depth and has an app that you can download your courses on and use offline.
Hello and welcome back to Flip Academy. Today we're going to look at integration part 2. This refers to spec points 2.5 and 3.5, so this is on paper 2 and 3. So the first step is to extending the idea of reverse differentiation to include the integration of e to the x 1 over sine, cos and sec squared. So again, these are just some results that you can remember that are pretty handy. So the first one is if you integrate sine of, again, some function that we don't know, then what you're going to do is you're going to do 1 over the differential of that function, and that's going to be cos f of x, and then of course the plus c on the end. So for example, if this was sine x squared, then that would equal 1 over 2x cos x squared plus c. There's a few more you have to remember, so you also have to remember the one for cos. So if you have the integral of cosine of some function, then that's going to be negative 1 over the differential of sine f of x plus c. So again, if you remember rightly back in the differentiation video, when you differentiated sine, so this would be the negative one, this would be the positive one. So if you remember, when you differentiate sine and you got cos, it was positive, the sign didn't change. When you integrate, the sign does change, it becomes negative. And likewise, when you differentiate cos, you got negative sign, so now you're going to do the opposite. So cos, the sign will stay exactly the same for sine and cos. The next one we're going to be doing is sec squared. And again, some of these results are a bit tricky, but once you practice using them, they're not too bad. So if we have sec squared f of x dx, then that is going to be 1 over the differential of whatever that function is, tan f of x plus c. And lastly, actually not lastly, we have two more that we have to do. We have the integral of 1 over ax plus b, which we have used in a previous video if you remember rightly, but all that would equal is 1 over a times ln ax plus b. And then obviously the plus c as well. And lastly, if you have e to the f of x, just like differentiation, whoops, dx, you have 1 over the differential, and then the rest stays exactly the same, plus c. So the reason why these are really important so what I'd recommend you do is if you write down these results on a piece of paper, and whenever you do an integration question as part of your revision, you have them all just in front of you, and that will help you remember them, but it will also help you work out the answers to these integrations. So a lot of the integrations we're going to do today involve getting our equations into this form. So for example, if we have integrating tan squared, well, you can't integrate tan squared, right? Or at least we don't know how to. So what we're going to do is make it sec squared and integrate that. So that's the kind of tricks that we're going to be doing, okay? We're going to be trying to get our equations into these forms of equations that we do know how to integrate instead, okay? So that's a key thing. So the best thing for you to do is write these down, maybe even on like a small piece of paper, stick it on your screen, so whenever you're doing integration questions, you should have that to refer back to. Now, on to the first question. Using trigonometrical relationships in carrying out integration. So what does that mean? Well, it means using things like sine squared plus cos squared equals 1, or the sec and cosec versions of this. And it also means using things like the double angle formula as well. So you could use the cos double angle formula in order to work things out, because you can integrate cos, but integrating sine squared and cos squared is much harder, so you may need to use these trig relationships. So every trig relationship you know from before, so the double angle formulas, the addition formulas, the sine squared plus cos squared, and the cosec squared, and the sec squared one as well, all of those can be used in this integration. So We have an example question here from the June 2019 paper. Find the integral of tan squared 3x. Well, if I look back at my answers, I don't have tan squared here. And it's in it's not in your spec, right? You can't integrate that. So instead, I need to think, okay, I need to change this into something else. So I could change it into sine squared and cos squared, but we don't know how to integrate cos squared and sine squared. But we do know how to integrate sec squared, so how can I change it? Well, if we have sine squared x plus cos squared x equals 1, and I divide it by cos squared, the whole thing, I then get tan squared x plus 1 equals 1 over cos squared x, which is sec squared x, which, if you notice, is something we know how to integrate. So then tan squared equals sec squared x minus 1. Okay, so if I sub that into this equation now, what I'm trying to do is do the integral of sec squared x minus 1. Sorry, sec squared 3x. Then if we go up, what we have to do is differentiate the inside, do 1 over it. So if I differentiate this, I get 3. If I differentiate 3x, I get 3. So it'd be 1 over 3 tan 3x minus x plus c, and that will be your final answer for that one. Okay, so 3 marks, not too tricky. Again, you can remember these individual trig relationships here. I prefer just to remember the first one and derive the other two, because it's, the less you have to remember, the easier your exam's going to be. You don't have to rely on your memory. Pretty interesting one, might look a bit tricky, but again, think about what you can do. We can't integrate fractions like this unless they happen to look like this. Other than that, we can't actually integrate fractions. So, what we're going to do instead is I'm actually going to perform this division. So, we have the integral. E to the 3x divided by e to the x would give me e to the 2x. And that would give me plus 4 e to the minus x dx. And now I just perform the exact integral as intended. But of course we're doing this from 0 to 1. So, if I integrate e to the 2x, again, going back up to our example, we differentiate what's in the power, the exponent, and do 1 over it, and we keep the rest the same. So we're going to have e to the 2x, so 2x differentiated becomes 2, so it becomes 1 over 2, and then e to the 2x stays exactly the same. If I differentiate minus x, I get minus 1, so that'd be minus 4 e to the minus x. And then again, I'm not going to bother putting the plus c because we don't actually need it. So now we're going to sub in 1 and 0. So again, I do like to use the big square bracket still. Half e to the 2 times 1, so just half e squared, minus 4 e to the minus 1. Minus, and then we're subbing in 0. So remember, e to the 0 is just going to be 1, so we just have a half minus 4. And then we can just work out what that is. So that would be a half e squared minus 4e to the minus 1. And then a half minus 4 would be minus 7 over 2. So then minus over minus would become plus 7 over 2. Nice and easy, hopefully, once you, again, knowing the actual kind of formulas you need to remember and the integration results is key to this. If you don't know that, you're never going to be able to answer these questions properly. But again, that was 4 marks, which, I've done it in 3 lines, not too bad. Without using a calculator, find the exact value of, and then we have the integral between 0 and 2 of 4e to the minus x, e to the 3x plus 1. So again, I can integrate products, which we're going to do a bit later on with another spec point, but it's preferred not to integrate products, okay? So instead, I'm just going to expand the brackets. So I'm going to have the 4, right? Of course. I could always pull that out as well. I could pull it out front of the integration sign. E to the minus x times e to the 3x is going to be e to the 2x. And that's going to be plus 4e to the minus x dx. Again, integrated between 0 and 2. And then we followed basically the exact same steps as the previous question. So, differentiate 2x gives me 2. So now I'm going to bring that to the front as a fraction, so 4 over 2, so that just leaves it as 2 e to the 2x. That's going to be minus 4 e to the minus x, because again, if I differentiate minus x, I get minus 1. So 4 divided by minus 1 is minus 4. The rest stays the exact same. And I'm subbing in 2, and I'm subbing in 0. So again, I'm going to leave the staple brackets in, because I prefer them. E to the power of 2 times 2, which is 4, minus 4 e to the minus 2, minus 2 e to the power of 0, so it would be 2 minus 4. So again, we're going to have the exact same type of thing. 2 e to the 4 minus 4 e to the minus 2, and then 2 minus 4 is minus 2, minus of that would be plus 2. And that's 5 marks. Pretty good, I think. Again, not too shabby, I think. Okay, next question. So understand and use the trapezium rule to estimate the value of a definite integral. So the trapezium rule, if you were to visualize it, is when you just break up this curve into a series of trapeziums, and then you're adding all of their areas together. However, there is a formula for it, okay? Because the formula can kind of help you out here. So the diagram shows the curve y equals tan 2x between 0 and a sixth of pi. The shaded region is bounded by the curve and the lines x equals 1 over 6 pi and y equals 0. Use a trapezium rule with 2 intervals. Okay, so here is the trapezium rule. It's a bit of a lengthy formula. I'm going to write it in words because I find that the letters can be a bit confusing. So the area under a curve is equal to a half times the width of a strip So again, just to visualize what we're doing here, what we're basically doing is breaking this down to a series of strips, which would then be trapeziums, right? Which would give us an estimate for the area under the curve. So, half of the width of the strip multiplied by y1, which is the first y value, so first height. So in this case, it would be whatever this y value is here. It's just the first y value, okay? Plus 2 times all of the middle heights, okay? Plus the last height, and that's it. So this here is the last height. And this here is every single height in the middle. So let's say you broke it up into 5 strips. Your first height would go here. Your fifth height would go here. Your second, third, and fourth would be in here. If you had 6 strips, first height, sixth height, second, third, fourth, and fifth. Okay, so I'm going to call these the middle heights. Cool. So now we actually need to work out what these values are. So for us, we have 2 intervals, which means we're breaking this up into 2 strips. So for my formula, I'm actually not going to have any middle things here. They're going to go away. So the height, right, or h, which I'm going to call the width of the strip, right, is just equal to 1 over 12 pi. Where did I get that from? Well, if I'm splitting this in 2, so again, what I can do is actually clear this up a little bit to make it a bit clearer for what we're actually doing. So, what we're actually doing is we're going to cut this directly in half so it's 2 big trapeziums, okay? Now if that's a sixth of pi, this would be 1 over 12 pi because it should be halfway between. Keep in mind the strips have to be equal in width. So my width is going to be a 12th of pi. If you ever want to know, all you need to do is work out the biggest x coordinate and divide it by the number of strips you have. And that will be all you need. Now the next thing I need to do is actually work out all of my y values. So let's draw a little table. We're going to do x, y, and the x values I need are at 0, a 12th of pi, and a sixth of pi. Those are my three heights, okay? So I'm going to have this, this, and just one in the middle here, okay? So I'm not going to have all of the adding. I'm just going to have 1, 2, and 3. So again, this is going to be the height at 0, the height here, and the height here. That's my y1, my y2, and my y3, or, you know, you can call it the yn as well, okay? In terms of this formula here. So all I need to do is sub it into a value on the calculator. So you can just get a calculator up and use that. Or you can kind of work it out. So tan of 2 times 0, so that's tan of 0, which is obviously 0, which you can see from the graph. Tan of 2 times 1 over 12 pi would be tan a sixth pi, which is root 3 over 3. Right, because tan 60 degrees is root 3 as a sixth of pi, and then this would be a third of pi, which is root 3. Again, these are values you should know from GCSE anyway, so it's actually not too bad, but you can use a calculator like so. And then all we need to do is sub in all of these values into our equation. So my area is going to be a half times a 12 pi, open bracket, so I've done the width of the strip so far, y1, which is 0, plus 2, and the middle height, there's only one middle height, which is root 3 over 3, and plus root 3. And you enter all this in a calculator and you'll get your answer. So let's do that quickly just to demonstrate. So we have 1 over 2 times 1 over 12 pi I'm going to skip the 0 for obvious reasons. Whoops. So again, you're going to get a pretty ugly answer for this one, and that should be it. 0.378, I'm going to call that, to 3 significant figures. And that would be it. Again, it's a 3-mark question, not the easiest one to do in the world, but hopefully that makes sense. And now it says, find the exact volume of the solid formed when the shaded region is rotated completely about the x-axis. So we did this in the previous integration video, but just so you are aware, what you're going to be doing is integrating pi times tan squared, so times y squared. Okay, and we're going to be doing that between the values on the x-axis, so 0 and 1/6 of pi. So this is pi, 0, 1/6 of pi, and y squared is just tan squared 2x. And if you notice, we can use the exact same trick that we used back here to make it sec squared minus 1 instead, which is better. Again, you could write that out in full terms again, but I'm not going to. So this would be the exact same as sec squared 2x minus 1 dx. So the integral of that was, you would integrate that, so it would be a half tan 2x minus x between a sixth of pi and 0. And then you would times that out, which is a bit spicy. And we need to find the exact volume. So pi a half tan. So if it's 2 times a sixth pi, that's going to be a third pi. So I'm just going to write that instead to make it slightly easier on myself. Minus pi times half tan 0 minus 0. So this whole thing here is 0 because tan of 0 is 0, as we discovered back up here. So all we're left with is this little piece here, which honestly, leaving it like that, well, not exactly like this, but we can leave it in brackets is what I mean. So pi, and if you remember, tan of pi over 3, we didn't do, never mind, is actually root 3, right? Actually, we did do it because this one here. So it's just root 3, so it's just root 3 over 2. The over 2 comes from the half. So if you were to enter this in a calculator, you get the exact answer. Tan of a third pi is root 3, and then a half will be over 2. Minus a sixth pi. And that is your final answer. Again, 4 marks. These questions are quite short. It's just that they're very technical, so they can be a bit tricky to work out and do and all of that fun stuff. But hopefully that makes sense so far. Now we're going to get on to some really fun ones in a second, where we're going to have to deal with things like products and all of that fun stuff. So let's get on with it. So integrate rational functions by means of decomposition into partial fractions. Recognize an integrand in the form of k, f prime x, and f of x, and integrate such functions. So this is when you're doing things like ln and all of that fun stuff. Okay, so this one is pretty big. So let's get to it. If you have something like this, we can't divide these signs because one has x and one has x plus 1 over 6 pi. So what we need to do is use the good old-fashioned addition rule, which I mentioned we may need to use at the beginning of the video. So if we use the addition rule, that would make it sine x cos pi over 6 plus sine pi over 6 cos x over sine x dx. Now what we can do is we can actually cancel out sine x, and cos over sine makes, so in this case it would be, cos over sine would be cot x. Okay, so again what I did here is I just did the division, right? Sine x, and then you have cot x here. So half pi, quarter pi, and that would be cos pi over 6 plus sine pi over 6 cot x dx. Now, here's where things get a bit spicy. What we could do is work out the values of sine pi over 6 and cos pi over 6. So again, if you are using a calculator, you can just use this. So it's pi over 6 root 3 over 2. So here we have and do the same thing for sine. I didn't need to delete the whole thing, but pi over 6, not 2, a half, right? So what we need to do is now integrate this, right? Now the first part is pretty easy, yeah? The first part, all I need to do is add an x after that because it is a constant. But the tricky part is integrating cot x. Well, if I look at cot x, right, that is the same as cos x over sine x. Now, this thing here, if you were to integrate it, it just becomes k ln f of x. Because if you remember, when you differentiate ln, right, you differentiate what's inside and put it over the original thing, right? So for example, if you had ln 2x and you differentiate it, you would have 2 over 2x. Okay, so likewise, if you were to integrate it, it would go backwards. Okay, sine and cos. Cos is the differential of sine, right? So we can immediately just call that ln, so the half stays there, ln sine x right? Because again, if sine is sine, the differential of it is cos. If you have a differential over its normal form, you can just write ln of the normal form. Okay? So in this case it would be k ln f of x. So again, differentiate sine, you get positive cos. So what if it was sine over cos? Well, in that case you'd have minus ln cos x, because obviously the differential of cos is negative sine, not positive sine. I hope that makes sense. But that's what they mean in terms of this question specifically. Then all we need to do is sub in our values. So again, we can just use a calculator for all of this, or if it's you're going to get into the habit of not doing it with the calculator, that's totally fine. Since it's exact value, you never really have to work it out, if that makes sense. Perfect, okay. So either way you want to do this, I mean, for the first one you're going to have to just simplify it to root 3 over 2 over 4 pi. But what we can do is actually, and what I think is easier, again, if it's calculate aloud, just do this minus this, because we know that that's going to be put together. So root 3. You can do this algebraically the slightly longer way. I'm just trying to save a bit of time for us. Fine. And then minus pretty much the same thing. Pi. Okay, never mind. They won't give us a answer. My bad, that's a bit of a waste of time. So we have root 3 over 4 pi, and then sine of that plus half ln. Sine of a half pi is 1 minus root 3 over 8 pi plus a half ln a quarter would be root 2 over 2, so half. So that bit here would just be root 2 over 4. Actually no, sorry, you can't do that just yet. So times ln root 2 over 2. Okay. So now the question is if you want to kind of bring it together or not. So root 3 over 4 pi minus root 3 over 8 pi would be root 3 over 8 pi. Because again, if you subtract them, since they're twice as big as each other, it would just be the middle value. And then ln 1 is actually 0, right? Because again, if you remember what ln's do, they rearrange the power formula to tell you that e to the base of something gives you 1. The only thing that would do that is 0, so that just disappears. And then all you're left with is minus half ln root 2 over 2. That was a pretty spicy question. Hopefully that's okay. So once again, we have done something very similar to this before. If you look back, this is the same as just integrating sec squared x minus 1 dx, which is equal to tan x minus x plus c. So nice and quick. Now, parts. Integration by parts. This is a huge part. It can be fairly tricky. So essentially, what parts is if you have two separate functions multiplying each other. So as you can see here, we have 1 over x cubed, and we also have ln x. So we have two separate x functions multiplying by each other. So what this looks like in terms of integration by parts is if you have v multiplied by the differential of u, and that's the same as just writing uv minus the integral of u dv dx with respect to x. Okay. Now this is where it can be helpful to use the notation that u prime would just equal du by dx, right? But again, you don't have to. So if we have these two pieces, I'll call them, we can label one of them v, one of them du by dx. And what we have to do is really be careful on which one we label. It's not always that the first one is v. So how do you decide? Well, what you want to do is, if you notice, this end bit has another integral. So we have to integrate again once we're done, right? Now what we don't want is to get parts again, right? Because then we have to do the whole process again. And if there's parts again, then we have to keep going. That's why I said when we have the product of two things, we want to try and make it so we don't have the product. Because if we do, it becomes very tedious. And sometimes there are things you can't integrate by parts. So for example, if you had e to the x multiplied by e to the x squared, and you try to do it by parts, it's impossible. It just goes on forever and ever and ever and ever and ever, right? Because e to the x stays the same. Using some hindsight, I'm going to say that this will be v and this will be my du by dx. Why? Because v is going to be differentiated here, which makes it 1 over x. So I'm going to get 1 over x cubed times 1 over x. Well, actually not 1 over x cubed, I'm going to get the integral of that, right? But I'm going to get something over x times 1 over x, which is always going to give me one function instead. Okay, so I'm getting rid of ln. The other way to look at it is I have to integrate du by dx. Do you know how to integrate ln x? No. So you can't do that. So if you ever see a natural logarithm, that has to be v, because you can't integrate natural logarithms, at least at your level. So again, just to go over that, if you see a natural logarithm, that has to be v, because v is only differentiated, not integrated. So I'm going to write that out fully. This is how I lay out my work, right? And then I'm just going to work out dv by dx, which is just 1 over x. And then I also know that du by dx is 1 over x cubed, or if you'd like, you can call that x to the minus 3, right? Which means the integral of that is going to be negative a half x to the minus 2. Remember, you add 1 to the power, bring it to the front and flip it. So that's how I lay out my work. So let's actually do this integral. So I'm going to jump straight from here. I'm going to apply the parts rule. So we have u times v. So u is minus a half x to the minus 2 multiplied by v, which is ln x, minus the integral of u, which again is minus a half x to the minus 2 multiplied by dv by dx, which is 1 over x. So now all I need to do is work out what this thing is, and I'm done. That is the same as the integral, so remember this is 1 over 2x squared, minus 1 over 2x squared, multiplied by 1 over x. So again, I'm taking very small steps to make sure you guys are completely fine with this. You are more than welcome to skip some of these steps. Which actually I should probably leave, now that I think about it, as 1 over 2. So again, we're going to add 1 to the power, flip it to the front, and then do all that business. So we're going to have plus a quarter x to the minus 4. Because again, when we bring the power down, it's going to be minus 2. Bringing that down, or to the front, it's going to be positive again. And then technically we need a plus c. So subbing this in, minus a half x minus 2 ln x minus a quarter x to the minus 4 plus c. If you're wondering why the c stays plus even though I've times it by a minus, because again remember we still have this minus here, that bit catches people out too, it's because it's a constant, so it doesn't matter if it's plus c or minus c. You can write minus c if it makes you feel better though, that's completely fine. Okay, one last integration trick, and look at that. That's a beautiful question, isn't it? 7 marks. Okay, the last integration trick that you need to know for at least this part of your spec, is substitution. So sometimes we have something like this, and like I mentioned before, we hate with a passion fractions. Integrating fractions is basically impossible, okay? At least on face value. So what we like to do is use a substitution, right? So I could sub this in right now. Okay. Can't integrate that though either, can I? So I need something for e to the 3x. Well, I'm going to look at my substitution. Can I make this e to the 3x equals? Well, I can make it e to the x equals fairly easily. And what is e to the 3x? It's just e to the x cubed. So I'm going to cube both sides. Okay, so now I do it. So now I have u minus 1 cubed over u dx. Okay, now I can start integrating, right? No. Because look, I have u's and I'm integrating with respect to x. Well, that would just be add an x on the end. But u is a function that depends on x. Okay? So what we need to do is we actually need to substitute in for x. So the other thing you need to remember to do is to differentiate what you're subbing in. So now we have du, we can substitute that into here and we're good to go. We need to differentiate with respect, sorry, integrate with respect to du now. So dx is equal to du over e to the x, which you could write as du e to the minus x as well. So now my value is but oh no, I have yet another e to the x. But if you notice, e to the x is just u minus 1. So now all I have is, again, 7 marker, right? I'm taking this in very small baby steps. You might notice it may have been more efficient to do it another way, in the sense that you do this substitution here first. And it is more efficient. The reason why I'm showing you this way is to show you the individual pieces, okay? So subbing this in first is actually the most efficient thing to do. But we can cross out. Okay. Now we have the integral u minus 1 squared over u. But you can't actually do this yet, right? So instead what you're going to do is expand the top bracket. So you get u squared minus 2u plus 1 over u du. And then you're actually going to do the division, because remember we just want to do the division when we have a fraction. So u minus 2 plus 1 over u. Now integrating this becomes trivial. Add 1 to the power and divide it by the new power, so that becomes squared, so it becomes half u squared minus 2u. And remember, if it's 1 over x or 1 over u or whatever, it just becomes ln. And then obviously you have your plus c. If we look at the answer, we're very close to what we should do. All we need to do now is sub u back in. Okay, so 1 plus e to the x. Keep going. And if I look back at my answer, it's getting closer, right? ln 1 plus e to the x, I have that. And I have some of the other pieces. So now what I need to do is actually expand them. So now I have a half. You have the 1, you have 2e to the x you'll have, and you'll have e to the 2x minus 2 minus 2e to the x plus ln 1 plus e to the x plus c. I have, actually I'll do it in steps. So a half of 1 is 1 over 2, minus 2 would be minus 3 over 2. We then have a half of 2 e to the x, so we have e to the x minus 2 e to the x, gives me minus e to the x. and then you have a half e to the 2x plus ln 1 plus e to the x plus c. So now if I compare this to my actual answer, I have the half e to the 2x, I have the minus e to the x, right? But I don't have this thing, and I don't have a c, because what they've done is they've said that k is equal to c minus 3 over 2, which immediately just gets rid of these two parts here. Gets rid of them. So now we just have, if we want to write it in order, put the e to the 2x first. So a half e to the 2x minus e to the x plus ln 1 plus e to the x plus k as shown. And that is it for integration for this part. So again, hopefully that's all okay. It's not too bad once you practice. It is fairly tedious though, so the questions are pretty long, but I'll see you in the next one anyway.